So exercise about the mass spectrometer and ionization energy. I'll start with question 14. Question 14, MCQ. The mass spectrum of a sample of an element is shown. You can see here the relative abundance is also given. What is a atomic mass of an element? Look, when you check this, like you need the atomic mass of this element. Now it's giving peaks in different regions. Like it is giving a peak in this region, like 31, 32 region, and there's also a peak in another region. Now, how to identify which peaks you should use to work out the atomic mass? So, if first we cannot take all of them. Why we cannot take all of them? Because like if it was like when we say we have different isotopes, so but they should have a comparable mass. So if different isotopes were even there, like if it was having 4 isotopes, then the peak should be nearby, like close to each other. It's not like 2 of the peaks are in the range of 30 and 40 and the 2 of the peaks are in a range of 60s and 70s. So it means what might happen, maybe these peaks are due to removal of 2 electrons. Like I cannot have, like if I say chlorine is having 2 isotopes, one is 35, another one is 37, but it cannot have an isotope of chlorine 70. That is totally wrong. Because whenever we have isotopes of the element, they should have a comparable mass, like in the same order. So what this give an idea, maybe what might happen, maybe 2 electrons, the mass spectrometer, we consider that only 1 electron is removed, but what might happen, maybe 2 electrons are removed. That's why the peak become half. So we will ignore these two. So the one which is the highest one, we'll compare these two now to work out the average mass of the atomic mass of this isotope. So it cannot be around like 40, 42 or 48. Like first thing, it cannot be around, this number is not at all possible. So what we'll take only these two. So when we take this value, so each one is representing like 10 boxes equals to 1. So each is representing 10 boxes equals to 10. So each is representing 1. So this one be 41, 2, 3, 4, 5, and 6. So this is 46. And the x-axis, 10 is representing 10. So each is representing 1. So this is 63. So it will be 63 times 46 plus this one is 20. So this will be 20 times 65 because like 63, 4, 5. And then what number we divide, because the first value, this was 46 and then 20. So what we'll divide, we'll not divide by 100 here. What we can divide, we can also divide by 66 to take, because like one is 46, another one is 20. So we can divide them by 66. So what's the answer here? When you take an average, because it's like divided by the total abundance or total sum of percentage abundance of each isotope. When you simplify, what's the final answer? 63.6. So 63.6, we check which option it matched. So it matches with option C. So why I did not divide with 100? Because so the rule is like we have the percentage of the isotope, like in this case, it was 40 and the mass was 63. Plus the percentage of the other isotope was 20 and the mass was 65. So when we divide with the sum of the percentage. So here 40 plus 60, so 40 plus 20. So what it will make, it will divide by 60. Or if it was 46 Like one was 46, another one was 20, so we divide by 66. That's why C is the right answer. Is it clear in this case? Any doubt? The next question, which species could be responsible for the peak at 32.5? So how we know? Look, what is the mass to charge ratio for sulfur? The mass is 32 and the charge is +1, so 32 divided, so it will give a peak at 32. What about copper 2, which is 63, so it will be 63 divided by +2. That will be 31.5. But 65 divided by +2, that will be 32.5. So C will be the, and this will be 98 divided by +3. So it will match with option C. Like C is responsible for a peak at 30, because mass to charge ratio, the total mass divided by charge. Which ion does not have the electronic configuration as shown? Like 2, 4, 6, 8, 10. The total, like this is 2, 2, 6, 2, 6. So means 18. Potassium atom is 2881. When it loses electron, the configuration will be 288. So it will be 18. For calcium, it is 2882. When it will lose electron, it will be 288. When we talk about titanium and scandium is 23, titanium is 22. Like when you check the periodic table, in exam, you will have the periodic table. You just have to use for the proton number. Like here's the periodic table. So we have titanium is there 22 and scandium is there 21. So what we want, the question is which is not having a 2, 8, 6, so 18. So titanium, when you check, the titanium is 21 when you check the periodic table. Sorry, 22. When you check the periodic table, it is 22. When it will form a titanium ion, it will be 20, not 18. And when you check a scandium, so scandium is 21. So when it will lose 3 electron, it will be 18. Calcium atomic number is 20, it will be 18. Potassium atomic number is 19. When it loses potassium +1, so it will be 18. So question is, which is not having this configuration? That is titanium. Because like titanium is 22, when it loses 2 electron, it will become 20. So if it becomes 20, it won't have this configuration, because this configuration is for those elements, those ions which are having 18 electrons. So it is for potassium, this is for calcium, this is for scandium, but not for titanium. In question 16, what is the electronic configuration of a nitride ion? So nitrogen is 7, but it nitride ion, so it will turn into 10. So for 10, it will be 1s2, 2s2, 2p6. So D should be the right answer here. So question 17, which equation represent the third ionization? So which one is representing a third ionization energy? So When you check here, 2 electrons are removed when we are removing the third electron from a gaseous state. So ionization energy means energy needed to remove electron from a neutral gaseous state. So here, this is representing the third ionization. So this is representing a third. This one is actually representing the fourth ionization. This is not at all correct. This is representing a fourth ionization, like fourth electron is removed. Structure question. This question is about the structure of atom state. What is meant by orbital? So you have to learn the definition of orbital. Orbital is actually a region within an atom, that is 1 mark, which can maximum hold 2 electrons in opposite spin. So you have to learn this, the standard definition of an orbital. Like S is one orbital. P is not orbital. P is a subshell. And this subshell contains 3 orbitals, px, py, and pz. D is again, it's not an orbital. D is a subshell. S is a subshell as well as an orbital because it contains only 2. So D is having dx, dxy, dyz, dzx, dx square minus y square, and dz square. So orbital means it is a region within an atom. So when you say region or inside atom, you will score 1 mark. And the second part, it contains two electrons in opposite spin. Contain maximum 2 electrons in opposite spin. That is the second mark. Then state the shape of S and P orbital. So what is the shape of S orbital? S orbital is spherical, where P orbital is dumbbell in 3 dimension, Px, Py, Pz. So how the marks are distributed? You will mention S are spherical, where P are dumbbell shaped. The next is describe what can be deduced about the electronic structure of a sodium from its successive ionization energy. A 3-mark question. So what we can deduce from the sodium, from the ionization energy, from their ionization energy first, when you write the electronic configuration of a sodium, it is 1s2, 2s2, 2p6, 3s1. So from the successive ionization energies, we can deduce that it will have 3 shells, because when we have the ionization energy and the number of electron removed graph, the first ionization energy will be lower, the second will have a greater gap. So from the successive ionization energies, we can deduce that it has 3 shells. That is 1 mark. And second mark is for writing a configuration. And the third mark, how we deduce it has 3 shells, because there will be 2 jumps will be there, 2 big jumps when we move from third shell to second shell, or we move from second shell to the first shell. So first mark, when you mention the sodium is having 3 electron shells, the second mark is for writing an electronic configuration, and the third mark is for saying that there will be 2 big jumps, which indicate that there is a shell changes from third to second and from second to the first. Then the log of fourth ionization energy of the 6 elements are given in the table. Plot the graph. You have to plot these results. This part is like plotting, like marking the axis, x-axis and the y-axis. For x-axis for the elements, like you have oxygen, you have fluorine, you have neon, then you have sodium, magnesium, and aluminum. And the y-axis for the log of ionization energy, you don't have to start with, because it's like 3 to 4 is there. So you can start your axis. It's not like you should start with 1. You can start with, say, 3.8 you can start with, as the value is to start. So this can be 3.8, 3.9, 4.0, 4.1, or for a greater difference, so 3.8, 3.9, 4.0, 4.1, like 10 boxes. And when we sketch the results, how the results will appear, the values are given to you like 3.87 for oxygen. I'm roughly sketching it. I'm not using the exact value. Then fluorine is 3.92. Then neon is 3.97. Sodium we don't have. Magnesium is about 4. And aluminum is there 4.06. Somewhere. So this is what you will have, like a sketch of the graph. But you will, and then use the graph, estimate the fourth of sodium. So fourth ionization of sodium, because as you can see, it follow a pattern. So what should be the fourth ionization energy of a sodium? First, you will work out the position where we'll get sodium, like somewhat here, we'll get sodium, but this is log of ionization energy. So log of ionization energy example, say it is the log of the ionization energy example, say this is 3.9. I need ionization. So when we need ionization energy, we take anti-log, or simply anti-log means 10 power. So 10 raised to the power of 3.99. This will give us the ionization energy. Like log ionization energy is 3.99. I need ionization. So when log move other side, it become anti-log or 10 power. So this will become ionization energy of this. So when we simplify, it will be 9,772. So this is how we convert the log of ionization energy to ionization energy. And suggest why the fourth ionization energy of neon and sodium are similar in magnitude, even different elements are there. What is the reason? Because the fourth ionization, we are removing the electron from the same shell. Like when we remove electron from neon, the fourth electron from neon or from sodium, we are removing from the same shell. That's why their ionization energies are comparable. So when we remove electron from the same shell, the ionization energies will be comparable. So this is mass spectrometer and ionization energy.